Hi everyone, my name is Chuan Longzhou. My topic is nonlinear analysis of reinforced concrete slabs under high-cyclical fatigue loading, and my supervisors are Dr. Jaina and Dr. Hu Zaifa. There are 5 main contents in this presentation, including introduction and literature review, research limitation and object methodology, results and discussions, and the conclusion. Now we are going to the introduction. Existing research has shown that long-term fatigue loading can result in decreased overload structural stiffness, insufficient residual strength, gradual development of concrete cracks, and the brittle fracture failure of steel bar, all of which can compromise the safety of the structure. You can see them from the figure 1. Therefore, the predicting and evaluating structure defects and damage, as well as maintenance and reinforcement, have become important means of preventing structural damage. Non-destructive testing is an advantageous method for evaluating the health of structure with interrupting their normal use. Vibration testing models, such as model testing and model analysis, are effective ways of monitoring structural health and has been widely used. However, comprehensive finite element model research is still lacking in analyzing fatigue damage on structures without relying on experimental data. Thus, it is essential to develop a numerical model to evaluate comprehensively the damage suffered by structures under high cyclical fatigue loss. Literature review. For this part, we focus on the fatigue performance of concrete theory bars and the monitoring technologies. For concrete, fatigue loading can induce residual strength accumulation of concrete, resulting in a continuous increase in the deformation of the structure and the spread of cracks. It was found that the elasticity module and degrades as the number of cycles increase, and the stress level substantially impacting the fatigue life of concrete, which saw as the stress level increase. At the same time, the fatigue life of the specimen started at high frequency decrease. For steel rebars, the PM study showed that the cumulative fatigue damage to the reinforcement was linear, and the action of steady high cyclical stress amplitude. Under the action of steady high cyclical stress amplitude, the elastic module of the steel bars remains unchanged, but their cross-sectional area gradually decreased due to the formation of microcracks, resulting in their instantaneous brittle fracture. For the monitoring technology, the non-destructive testing approach are advantageous for monitoring structure because they provide an efficient and precise examination of structures without affecting their functionality. The model testing approach not only enables the detection of damage but also the identification of its extent, location, and subtlety. Measuring the faulty performance of structures is critical of reducing their damage and ensures safe operations. However, accurate local damage area location before testing is difficult, time-consuming, and requires sufficient space to accumulate inspection devices, which is not always feasible. Therefore, global damage detection mechanisms are needed that do not rely on the damage data from local determination. The limitations. Number 1. The available information does not enough quantify the structural stiffness of vertical structures in relation to the structural integrity and stability of existing structures. Number 2. There is no limited information addressing the effects of low cyclic loading and high cyclic loading on structures using the vibration-based NDT approach. Addition, the implementation of a nonlinear FE model to compute the high cyclic faulting vibration behavior of RC slabs remains unclear, so we aim to assess the faulty performance and the dynamical progress damage behavior of reinforced concrete slabs under high cyclical faulty loadings using nonlinear FE analysis. The methodology. This study includes the following methodologies. The research involved using the nonlinear FE analysis model to evaluate the faulty performance and the dynamical process damage behavior of RC slabs under high cyclical faulty loadings. It includes the model test and the faulty loading test, model test, static loading test, and the last is the model test. The following details of FE are presented in detail from the modeling process, boundary conditions, and the mesh sensitivity analysis. Firstly, the key to the modeling process is the selection of the suitable concrete and reinforced modules, the prediction of concrete reinforced life, and the argument of the modules. Next, we adapted the same boundary condition as for the test. Loading was also carried out in the same way as the test. Thus, the maximum and the minimum loads was 16.5 kN and 20 kN respectively. The models were mainly calculated for 1.5, and 2 to 4 million cycles. Prior to the calculation, a mesh sensitivity analysis was carried out to ensure most accurate prediction with the shortest computing time. Prior to the calculations, a mesh sensitivity analysis was carried out to ensure most accurate prediction with the shortest computing time. As shown in the figure 7, the overall bending moment, overall deflection, and the curvature of the default RC slabs was considered in the current investigation. The faulty stiffness was calculated by establishing the equation for vertical stiffness through the geometrical relationship between the vertical loading moment and the radius of curvature. This part is about results and discussions. The FE module is validated against experimental test data. The verified FE module is subsequently utilized to simulate the dynamical vibration feature of acid stress exposed to high-cyclic vertical loadings. The investigate dynamical response are natural frequency, motor stress, and the stiffness of acid stress. The validation of the natural of the numerical simulation. Firstly, we calculate the residual strength of acid stress under 1 cycle, 1 million, 1.5 million, and 2 million cycle loadings. The results shown in the figure A. It can be observed from the figure that the general FE simulation could precisely predict the experimentally observed axial load deflection curves of acid stress. Secondly, we calculate the model test of vertical and damaged acid stress. Comparison between FE and experimental results in terms of natural frequency and model stress figure and damage spikes are shown in table 2 and table 3. Besides, we did the correlation analysis with above data. The minimal value is 1.9655, so we can make sure that the developer FE simulation could predict the modal stress and natural frequency of specimen with accessible accuracy. Finally, we extend the analytical results from 2.5 million to 4 million loading cycles. The results show that the same variation as those subject to smaller loading cycles. Hence, the modal stress is independent of number of loading cycles. Under the same loading cycle I, the damaged spike's natural frequency was lower than those of vertical specimens. Besides, the natural frequency was reduced by increasing the fatigue level. Vertical damage evolution of steel rebars and concrete. It could be observed from the stress and strain of concrete and steel rebars that the overall strength of the curve can be divided into 3 strengths: initiation, steady response, and failure. Among the 3 phases, the durations of start and failure were relative beliefs, whereas the stable phases accounting for more than 93% of the entire vertical lives. Throughout the whole vertical loading cycle, the strain of the steel rebars grew slowly within the first 2 million cycles, then intensified quickly between 2.5 and 4 million cycles, as well as the tensile strength of concrete developed rapidly, causing cracks to propagate to the comprehension zone. as well as the tensile strength of concrete developing repeatedly, causing cracks to the propagate to the compression zone, hence reduce the concrete compression zone and the bearing capacity of the arch slab. Correct development of arch slabs. Table 6 displays a comparison between FE and experimental correct pattern of arch slabs. It could be observed from the results that most cracks appear to be vertical and match the experimental cracking pattern. The vertical cracks initiate in the middle of the arch slabs adjacent to the loading points, where there was a pure bending portion of arch slab, indicating the beginning of crack distribution in arch slabs. It was found that the number of cracks increased as the cyclic loading increased. Besides, the initial vertical cracks gradually spread to the compression section of arch slabs along with the cyclic loading. As indicated in Table 6, increasing the loading cycle leads to an increase in the slab's curvature and a decrease in his residual strength. Sensitivity analysis of natural frequency degradation. We calculate the natural frequency of undamaged fatigue and damaged spikes from 1 cycle to 4 million loading cycles. The results indicate that the natural frequency of the fatigue and damaged arch slab decreased constantly flowing static loading, which could be attributed to the irreversible nonlinear behavior of concrete. Therefore, it could be concluded that an increase in the fatigue level leads to a reduction of the structure natural frequency and therefore its stiffness. The comparison of results revealed that for a particular model number under the same number of loading cycles, the natural frequency of the damaged spikes was lower than that of the fatigue specimen. Besides, the arch slab's natural frequency declined repeatedly during the earlier stage of the fatigue and thereafter slowed considerably at a later stage of high-cycle fatigue. The cumulative decrease of the natural frequency of arch slab increased, indicating the extent of the damage. Analysis of high-cyclic fatigue stiffness degradation. As shown in the figure 13, we compare the stiffness of arch slabs subject to low and high stress level from 1 cycle to 4 million cycles, as well compare the stiffness degradation between low and high stress at the same cycles. So in the figure 14, the stiffness reduced rate depends on the applied stress level. Compared with low stress level, the reduction in stiffness was more pronounced in high stress level conditions. It could be observed from the figure that the dynamical stiffness degradation rate was gradually increased by increasing the loading cycles. The reason could be contribution to the development of the damage in the slab, leading to the reduction of the concrete stiffness. This part is about the conclusions. And thank you.